Hi everyone, I'm Will, and in this video I'm going to be sharing a proof of Euler's theorem, as well as giving a bit of motivation for the theorem, and later trying to build a bit of intuition as to why Euler's theorem works. So, starting with the motivation, we like Fermat's little theorem because it allows us to easily find inverses for prime moduli. So it's not necessarily the most efficient way to find an inverse, but it guarantees that it exists, so we can go through this simple process of solving simple linear congruences. So working through this example, 5x is congruent to 7 mod 11. Fermat's little theorem gives us the fact that 5 to the 10 is congruent to 1 mod 11, which gives us 5 to the 9 is the inverse of 5 mod 11. The least residue of 5 to the 9 mod 11 is 9, so we can simply multiply both sides by 9, take the least residue, and we have our solution x is congruent to 8 mod 11. So we've seen the obvious utility of Fermat's little theorem, but we want to expand that to non-prime moduli. This brings us to Euler's theorem, section 9, theorem 1 in the textbook, that states for an integer m greater than or equal to 1 and an integer a that is co-prime to m, then a to the phi of m is congruent to 1 mod m. And we can see that this is a generalization of Fermat's little theorem because in the case that our modulus is prime, we have phi of p is p minus 1. So a to the phi of p is equal to a to the p minus 1, which is congruent to 1 mod p. Before jumping into the proof, we'll give a lemma that does a lot of the heavy lifting in terms of proving Euler's theorem. This lemma states that if a and m are coprime, and r1 through r phi of m is the set of integers less than m and coprime to m, then the least residues mod m of ar1 through ar phi of m are a permutation of the original set r1 through r phi of m. And the proof of this lemma has two parts. Since there are phi of m elements in our set of ARs, we need to show 1, that the elements of the set are unique, and 2, that the elements are all relatively prime to m. And once we've shown that it meets these two properties, we know that the set of ARs is a permutation of the set of Rs because, well, what is the set of Rs? Well, it's the set of phi of m unique numbers less than m and coprime to m. So, starting with the proof of uniqueness, we'll let ARI be congruent to some ARJ mod m for indices I and j between 1 and phi of m. And we'll note that there's no condition that requires these two indices to be different. Because a and m are coprime, we can cancel a to get Ri congruent to Rj. And by definition, since Ri and Rj are least residues mod m, we know Ri is equal to Rj. Then we take the contrapositive and we'll get if Ri is not equal to Rj, then ARI is not congruent to ARJ mod m. So we have this portion implies this, and then we take the contrapositive, which means not this, implies not this, and that's where we're getting this section from here. And then this is, proves the uniqueness of the elements of our set of ARs. Moving on to part 2. Proving that the elements of our set of ARs are all coprime to m, and we'll do this by contradiction. So let P be a prime common divisor of ARI and m for some index I. Since P is prime, we know that P has to divide either A or Ri. So P is either a common divisor of A and m, or it's a common divisor of Ri and m. However, by the assumption in our lemma, we know A and m are coprime. And we also know that Ri and m are coprime, since again, by assumption in our lemma, Ri is a least residue mod m. This contradicts our assumption in the start that we have some other common divisor p, so we have to conclude that ARI and m are coprime for all indices I. And this concludes the proof of the lemma. So, with the lemma out of the way, we can prove Euler's theorem. As I said before, the lemma really does most of the heavy lifting here. So by the lemma, we have the product of our r's, all the integers less than m and coprime to m, is congruent to the product of all of our ARs. Well, we can factor out phi of m ARs and then rewrite this as a to the phi of m times the product of our r's. In addition, since each r is relatively prime to m, their product is also relatively prime to m, so we can cancel the r's on both sides of the congruence, and then we'll end up with Euler's theorem. 1 is congruent to a to the phi of m mod m. So let's look at how we'd apply this to the same problem as earlier, but with a non-prime modulus. Again, we have 5x is congruent to 7, but this time we're taking mod 14 instead of mod 11, so 14 not prime, 2 times 7. Since we don't have a prime modulus, Fermat's little theorem won't apply, but we can use Euler's theorem to get 5 to the phi of 14 is congruent to 1 mod 14. And then finding phi of 14 is 6 by inspection, or by using the multiplicative property of phi. We have 5 to the 6 is congruent to 1 mod 14, which implies that 5 to the 5 is the inverse of 5 mod 14. And then we can find 5 to the 5 is congruent to 3 mod 14, and then multiply through to get x is congruent to 7 mod 14. And there we have our solution. And finally, I want to talk just a bit about the intuition behind why Euler's theorem makes sense, borrowing a little bit from group theory. We have this function phi of m giving us all the numbers less than m co-prime to m, which is clearly an important number, but why exactly does raising a to the phi of m give us 1, and why do we need that property that a and m are co-prime? So if you already have clear intuition of this in your head, feel free to skip the rest of the video, but personally I had a bit of a hard time grasping why this identity intuitively makes sense, so I wanted to share what I found by translating the problem into a relatively basic concept in group theory, and that is multiplicative groups mod m. So we can recall from abstract algebra that the numbers less than m and co-prime to m form a finite cyclic group under multiplication mod m. And then we'll also recall that the order of a cyclic group gives the number of times an element has to be exponentiated to return to the identity element, which is 1 in this case. We have by Lagrange's theorem that the order of a given element can be smaller than the order of the group, but it has to divide the order of the group. So while phi of m guarantees that we'll return to the element, we can in fact do it in fewer steps. So the restriction that our choice of a and m must be co-prime is just guaranteeing that we're only looking at elements that form a finite cyclic group of under multiplication mod m. We know the order of that group is phi of m, by definition, the number of elements that are less than m co-prime to m. So a to the phi of m is just guaranteeing that we've had a act on itself at least enough times to return to the identity element. Again, can be more times than necessary, but it's at least the correct amount of times. So I hope this didn't add unnecessary confusion. I know relating this to group theory helped me understand the concept a bit better, at least from a theoretical standpoint, so hope this made a bit of extra sense to you as well. All right, thanks for watching, and looking forward to seeing the other proof videos.